A metallic conduit or raceway can cause a voltage drop due to its electrical resistance. When current flows through the conduit or raceway, it encounters resistance from the metal, which causes a voltage drop. The amount of voltage drop is determined by the length of the conduit or raceway, the cross-sectional area of the metal, and the current flowing through it. The voltage drop in a conduit or raceway can be calculated using Ohm's law, which is expressed as volts equals amps times ohms. In this equation, volts represents the voltage drop in volts, amps represents the current flowing through the conduit or raceway in amps, and ohms represents the resistance of the conduit or raceway in ohms. The resistance of a conduit or raceway can be calculated using the following formula, which is expressed as resistance equals resistivity times length divided by area. In this equation, resistivity represents the resistivity of the metal in ohms per meter, length represents the length of the conduit or raceway in meters, and area represents the cross-sectional area of the metal in square meters. The resistivity of a metal is a measure of its resistance to the flow of current. The higher the resistivity, the more resistance the metal will have. The cross-sectional area of a metal is a measure of the amount of metal that is available for current to flow through. The larger the cross-sectional area, the less resistance the metal will have. Firstly, consider the material of the conduit. Different metals have different resistivities. For example, steel typically has a higher resistivity than copper or aluminum. Therefore, a steel conduit will generally have a higher resistance per unit length than a copper or aluminum conduit of the same dimensions. Secondly, the length of the conduit run directly impacts the voltage drop. The longer the conduit run, the greater the total resistance and, consequently, the larger the voltage drop. This is a linear relationship. Doubling the length doubles the resistance, assuming all other factors remain constant. Thirdly, the cross-sectional area of the conduit material plays a crucial role. A larger cross-sectional area provides more space for electrons to flow, reducing resistance. This relationship is inverse. Doubling the cross-sectional area halves the resistance. Fourthly, the amount of current flowing through the conduit directly affects the voltage drop. Higher current leads to a greater voltage drop, as dictated by Ohm's law. Therefore, circuits carrying high currents are more susceptible to significant voltage drops in the conduit. Fifthly, temperature affects the resistivity of metals. As temperature increases, the resistivity of most metals also increases. This means that the resistance of the conduit, and hence the voltage drop, can increase with temperature. This effect is generally more pronounced at high temperatures. Sixthly, the type of connection and bonding of the conduit sections is critical. Poorly connected or bonded sections can introduce additional resistance, increasing the overall voltage drop. Ensure all connections are tight, clean, and properly made to minimize this effect. Seventhly, consider using parallel conduit runs to reduce the overall resistance. If multiple conduits are used in parallel, the total resistance is reduced, leading to a low voltage drop. This is particularly useful for high current applications. Eighthly, be aware of the skin effect, especially at higher frequencies. The skin effect causes current to concentrate near the surface of the conductor, effectively reducing the cross-sectional area available for current flow and increasing resistance. This effect is generally more significant at frequencies above the standard power frequency of 60 Hz. Ninthly, regular inspection and maintenance of the conduit system are essential. Corrosion, damage, or loose connections can increase resistance and voltage drop over time. Periodic inspections can identify and address these issues before they become significant problems. Tenthly, when designing an electrical system, it is crucial to calculate the expected voltage drop in the conduit to ensure it remains within acceptable limits. The National Electrical Code, or NEC, provides guidelines and recommendations for maximum allowable voltage drops in various types of circuits. Now let's delve deeper into the practical implications of these factors. Suppose you have a 100-foot run of steel conduit carrying 20 amps. You can calculate the voltage drop using the formulas we discussed. First, determine the resistivity of steel, which is approximately 1.94 times 10 to the power of negative 7 ohms per meter. Then, determine the cross-sectional area of the conduit. For example, a 1-inch trade-size steel conduit has an approximate inner diameter of 1.49 inches, which translates to a cross-sectional area of approximately 5.4 times 10 to the power of -4 square meters, considering the wall thickness. Now, using the formula for resistance, ohms equals resistivity times length divided by area, you can calculate the resistance of the conduit. Converting the length to meters, 100 feet is approximately 30.48 meters. Plugging in the values, the resistance is approximately 0.109 ohms. Finally, using Ohm's law, volts equals amps times ohms, you can calculate the voltage drop. The voltage drop is 20 amps times 0.109 ohms, which equals approximately 0.218 volts. This example demonstrates how to calculate the voltage drop in a conduit run. However, it's important to note that this calculation is an approximation, as it doesn't account for factors such as temperature and the skin effect. To minimize voltage drop in your electrical system, consider the following best practices. Firstly, use conduit materials with low resistivity, such as copper or aluminum, whenever possible. Secondly, minimize the length of conduit runs to reduce the overall resistance. Thirdly, use larger conduit sizes to increase the cross-sectional area and reduce resistance. Fourthly, ensure all conduit connections are tight, clean, and properly bonded to minimize additional resistance. Fifthly, consider using parallel conduit runs for high current applications to reduce the overall resistance. Sixthly, regularly inspect and maintain the conduit system to identify and address any issues that could increase resistance and voltage drop. Seventhly, design your electrical system to minimize current flow in the conduit by using proper grounding and bonding techniques. Eighthly, adhere to the NEC guidelines for maximum allowable voltage drops in various types of circuits. Ninthly, use voltage drop calculators or software to accurately estimate the voltage drop in your system. Tenthly, consider the impact of temperature and the resistivity of the conduit material. The NEC provides tables and guidelines for directing conductor ampacity based on temperature. It is also crucial to consider the grounding and bonding requirements specified in the NEC. Proper grounding and bonding ensure that the conduit system is effectively grounded, which helps to minimize voltage drop and provide a safe path for fault currents. The NEC provides specific requirements for grounding and bonding conductors, equipment, and enclosures. Adhering to these requirements is essential for ensuring the safety and reliability of your electrical system. In summary, understanding the factors that affect voltage drop in a conduit or raceway is crucial for designing and maintaining a safe and efficient electrical system. By carefully considering the material, length, cross-sectional area, current flow, temperature, connections, and grounding and bonding techniques, you can minimize voltage drop and ensure that your equipment receives the correct voltage. Remember to consult the NEC for specific requirements and guidelines related to voltage drop, grounding, and bonding. Proper design, installation, and maintenance are essential for ensuring the safety and reliability of your electrical system. By understanding the factors that affect voltage drop in a conduit or raceway, you can design your electrical system to minimize voltage drop and ensure that your equipment receives the correct voltage. Furthermore, regular inspection and maintenance of the conduit system are crucial for identifying and addressing any issues that could increase resistance and voltage drop over time. By taking these steps, you can ensure the long-term reliability and safety of your electrical system. Consider the type of load connected to the circuit. Different types of loads, such as resistive, inductive, and capacitive loads, can have different effects on voltage drop. Inductive loads, such as motors and transformers, can cause voltage drop due to their inherent impedance. Capacitive loads, such as capacitors and electronic equipment, can also affect voltage drop by altering the current flow in the circuit. When designing your electrical system, it is important to consider the type of loads that will be connected to the circuit and their potential impact on voltage drop. Also, consider the use of voltage regulators to maintain a stable voltage supply to sensitive equipment. Voltage regulators can help to compensate for voltage drop and ensure that your equipment receives the correct voltage even when the voltage supply fluctuates. There are various types of voltage regulators available, including automatic voltage regulators, or AVRs, and constant voltage transformers, or CVTs. The choice of voltage regulator will depend on the specific requirements of your application. By understanding the various factors that can affect voltage drop in a conduit or raceway and implementing appropriate mitigation strategies, you can ensure the safe and reliable operation of your electrical system. Proper design, installation, and maintenance are essential for minimizing voltage drop and maximizing the performance of your equipment. The 2017 NEC provides detailed guidelines and requirements for voltage drop calculations, grounding and bonding, and equipment installation. Adhering to these guidelines is crucial for ensuring compliance with electrical codes and standards. It is also important to stay up to date with the latest revisions to the NEC to ensure that your electrical system meets the most current safety standards. Always consult with a qualified electrician or electrical engineer for assistance with designing, installing, and maintaining your electrical system. These professionals have the knowledge and experience necessary to ensure that your system is safe, reliable, and compliant with all applicable codes and standards.